sat never used, it started to deteriorate to a substantial degree. And another interesting thing happens when you do store nickel cadmium nickel metal hydride batteries. The first time you charge it, it exhibits a very strange behavior. So the bottom curve here is a normal charge cycle after the battery's been conditioned. If we had a battery that had been in storage and we plug in the charger, well, the voltage skyrockets and then it starts to go down. And if you have a voltage go up and then down, the battery charger, in this case, thinks that the charge is done because it's programmed to determine when this peak occurs, but it sees this peak occurring right at the beginning. So a battery that had been on the shelf for a while and it needed conditioning couldn't be conditioned with the actual charger that it was supplied with. So we would have to take this battery and plug it into a power supply and force this charge into it in the first cycle. Or as you see I did here, we charge it, the charger cuts out. It turns the charger off and on, it charges, the charger cuts out. They turn it off and on, it charges, they keep doing that, and then discharge it. And then the next discharge, the voltage is quite a bit higher than it normally is, and it still starts to drop. And so it cut out, I think even then it cut out before it should have. And finally on the third charging, then it has a much more regular charge curve. And then the fourth one is the big one that shows it's a more pronounced voltage peak. But this is something that we could do if a customer just had a battery and a charger that they stored over winter, and they plug it into charge, the charger goes green, but it's only put in an amp hour, and then they go to use their e-bike, they won't get any range out of it, and they'll think the battery's toast, when it just needs a prolonged conditioning cycle, but they can't actually condition it because the charger will terminate the voltage peak. So you can see just about every aspect of the battery is going to fall apart, right? Including something as lowly and simple as the fuse. There's not too much to comment here, except that sometimes it's not, especially with this style of fuses here, we have often cases where somebody, they're not getting any power from their bike, and then we would go and we'd measure the battery pack with the multimeter, and it would show 49 volts, and then you'd plug it in the bike, and there'd be nothing, and then you'd measure the voltage now, and it'd be 0 volts, or maybe 3 volts or something. And often when a fuse burns, it chars the plastic, and the charred plastic contains carbon and conducts enough electricity that the multimeter can actually pick off the voltage through that charred carbon. But as soon as you try to draw any current with the motor controller, the voltage immediately plummets to nothing. So we probably had about 2 dozen cases that things were stuck for quite a while. It's the same when the tabs came loose that I showed you before. Sometimes the tab will break loose, you have burned paper there, and so you measure the voltage and it looks good, but the moment you try to draw current, there's actually no continuity. Okay, so that was the first half of the presentation, which was all the nickel experience. How am I doing for time? What?
Keep on going.
Keep on going? Okay, I'll fly through. I'll try to get these guys a little bit faster. So, obviously, all the excitement is with lithium batteries. And when we first got into this in 2003, that's where all the excitement was. And it was just in the very early days you could get high-capacity lithium cells for electric vehicles like this. Lithium cells at 3 to 4 volts per cell instead of 1.2 to 1.5 for nickel. So you can use a fewer number of cells to make up the same voltage of battery pack. And as a result, you end up with a battery that's significantly less weight, a third the weight of NiCad, half the weight of nickel metal hydride. And they also have very ideal electrical characteristics. That for every amount of charge you put into a lithium battery, you get that same amount of charge back out of it. Not like the nickel ones, where you have to overcharge them in order to reach their full state of charge. And there's all kinds of variations of lithium. The 3 that we've seen the most use of in applications for electric bikes is a lithium polymer. And that's the lightest weight lithium that usually comes in a foil pouch. So it's not in a metal can. It looks almost like something you throw in a boil in water and then open it as a curry cake or something. Lithium manganese is, of the mainstream lithium that you get in laptops or other things, manganese is the safer one and the least prone to fire-related incidents. And then lithium iron phosphate is the most recent lithium chemistry to become widespread. It's significantly heavier than the other 2, but there's potential for it to have a much longer cycle life, which in a vehicle is an important characteristic. So just a quick summary of the characteristics of a lithium cell. So when you discharge the lithium, it starts off at about 4.2 volts. You drain it down to about 2.9 volts when it's flat. If you keep draining it, you'll get a little bit more out. If you drop it less than about 1 volt, you permanently damage the cell. If you drop it between 1 and 2 volts, you have to be very careful as you recharge it. So they don't like to be discharged below this point. Whereas the other nickel ones, you could drain them all the way flat, you can even reverse them, and there's chemical reaction that could absorb that current flow. And then when you charge lithium, it's just ideal. You just put a current through it, and the charging curve is basically the discharge curve in reverse. So it starts off with lower voltage, climbs up quite steadily, and then once it hits 4.2 volts, it stays at that point. And it charges. It takes exactly the same number of amp hours to recharge it as you got out when you discharged it. And lithium batteries, lithium is also assembled into packs by putting cells in series, and also suffers the same fate. They can be at different states of charge for whatever reason. So they can, different ones can self-discharge it, or because of different temperature variations in the battery pack. So if you take a lithium battery that has cells in it that aren't all balanced, so some cells are a little bit more charged than other cells, and then you charge it up, the cells will climb up, and one cell will hit this full 4.2 volt burst. If this was a nickel-based battery pack, we would keep charging it. These other cells would continue to top up, and this one would just get warm, and then there would be a chemical reaction that would take up the extra current. Now, lithium, that doesn't happen quite so well. So it continues to absorb those electrons and then causes pressure buildup and internal swelling. Some batteries, especially from 4 or 5 years ago, could actually become quite catastrophic and pyrotechnic if you overcharge them for too long. But even bringing them up to 4.3 or 4.4 volts causes noticeable deformation and warming within the cell itself. So you can't let this happen. You can't just, a lithium battery pack won't naturally balance itself the same way that a nickel-based battery will. The same thing is true when you're discharging it. So say we started with those same cells that are kind of in mid-state of charge, drain the battery pack. Well, this one's going to go flat first. If we keep draining the whole battery pack, that cell is destroyed. It'll drop down to 0 volts. Well, these ones are still, at 3.3 volts, 2.9 volts, 3.6 volts or something. And then you've irrecoverably damaged the one that you drained all the way to 0 volts. The solution to this is that every lithium battery pack needs a battery management system, as we call it BMS. The BMS sits there and actually individually monitors what's going on at each one of those cells. So normally when we see a battery, all we see is this terminal here. That's the output of the battery pack. And we're not looking at all the 1.2 volt or 3.7 volt little cells that make up the entire battery. But in a lithium, it's essential that somebody or something's looking at those, because you can't let any one cell overcharge or overdischarge. And that's the BMS circuit here. And you can see it's got drains and a switch, and it can switch off the output of the battery if it senses anything going wrong with the cell being overcharged or overdischarged. Better BMS circuits can not only cut off the charging and the discharge, but when you are charging it, if it senses that one cell is more charged than the rest, it can allow the battery pack to balance. And it can replicate the functionality that's lost, that the nickel can do just intrinsically with the chemistry. This thing does it externally via electronics. So now we've charged up this battery. This cell has reached full charge. Well, these ones all still need to top up. So the battery management circuit, it connects a little resistor between the terminals of that cell and allows it to bleed off the extra current. So now the extra current that would normally cause us to overcharge gets bled off to the battery management circuit. The battery management circuit gets warm, so they can only bleed so much current at a time, but it's sufficient to bring cells that are normally all at different states of charge to one that's in a balanced battery pack. Another style that we've seen quite a bit is where they'll use, instead of a resistor to drain off that cell, they'll actually drain the overcharged cell into a capacitor. And then